In our previous video, we have reformulated the second law of thermodynamics that was first introduced, that the entropy of the universe is always the entropy of the surroundings plus the entropy of the system, and this summation is always to be positive. However, we saw that in some cases the change in entropy of the system can be positive, in other cases it can be negative, so just by looking at the variables of the system we cannot tell which process is going to move forward and which processes are going to move backward. A way to introduce this factor, the entropy of the surroundings, into our system is by using enthalpy. We have said that a new variable such as the change in Gibbs free energy will give us exactly that, because when you have an exothermic process, that it means it kicks out energy that will probably increase the entropy of the surroundings and therefore will make the whole entropy change of the universe positive. So let's try to understand a little bit more how this equation works. In this case, you are given excuse me, you're given this typical, what that would be from a gas to a liquid, so we call this a condensation process, and we are asked to decide what signs of change in enthalpy and entropy a condensation process have. Well, if you are condensing, it means that you need to remove energy from gas for it to become liquid. There has to be some heat leaving the system. If the heat is leaving the system, this is an exothermic process. So think of it as if the heat is leaving the system, probably the entropy of the surroundings will be positive. So this is why we can use the enthalpy, the sign of the enthalpy, to describe if the entropy of the surroundings will be positive or negative. However, notice that the disorder of a gas is much larger than the disorder of the liquid, so therefore the change in entropy is negative. That is, the disorder of liquid minus the disorder of gas, final minus initial, disorder of gas is larger. This means it's going to be negative. Okay, so is delta G going to be positive or negative? Well, enthalpy is negative and entropy is negative. However, negative and negative is positive. So you're adding something that is negative and something that is positive. This means that we cannot know right away if delta G, if the change in Gibbs free energy, is going to be positive or negative. What we know is that the temperature can change the sign. That means at higher temperatures, the factor of entropy, the TWS, will have more importance. Therefore, this will make, and remember that this is positive, it will make the change in Gibbs free energy positive. In other words, not spontaneous. So at higher temperatures, this factor that it happens to be positive increases. You decrease the spontaneity, if you will, by making delta G positive. At lower temperatures, what happens? At lower temperatures, you decrease the influence of entropy, which is negative, and the factor of enthalpy suddenly becomes more important. So at lower temperatures, your delta G will be negative and therefore more spontaneous. So here you have a process in which, while the signs of enthalpy and entropy do not change, the sign of delta G, the sign of Gibbs free energy, can change depending on the temperature. And one can build this table in which, depending on the sign, you can see what will happen to low temperature and high temperature. The case of condensation is this one here. This is not a condensation. It's freezing of water, but it's similar. It's similar because we said that the change in enthalpy is negative, but also the change in entropy is negative. So at low temperature, as we discussed, at low temperature, what you have is the delta H, whatever the delta H says, that's going to be the sign of your delta G, because at low temperature, the entropic factor is less important. So at lower temperature, the process is spontaneous, which should make sense, right? If we are trying to condense a liquid or to condense a gas or to freeze a liquid, what you want to do is to lower the temperature. So intuition and equations say the same. Notice that there is a combination when this is positive, when the enthalpy is positive and the entropy is negative, that is non-spontaneous at all temperatures. There are some reactions that are non-spontaneous. You may have a little bit of a little bit of products, but you will never have a majority of products. And so temperature cannot change it. Notice that a change in entropy of the system and endothermic means that you are decreasing both the entropy of the surroundings and the entropy of the system. That goes against the second law of thermodynamics, so the process is non-spontaneous. You will see that, so in this case, you also have a change in spontaneity depending on the temperature. So these two cases, the cases in which the enthalpy is negative and entropy is negative, or the enthalpy is positive and the entropy is positive, these two cases depend on temperature. However, when the enthalpy is negative and the entropy is positive, it's always spontaneous, and the spontaneity, while it may depend on the temperature in the sense that it may be more or less negative, it is always negative. So let's try to solve a question. I'm going to go back to that graph in a minute, but I want to first make sure we have this issue understood. In this case, we're being asked which of the following is always spontaneous. Well, to do that, it means that we are looking for the sign of enthalpy and entropy. If we want delta G to be negative, it's because we want delta H to be negative, and delta S, careful, there's a negative here, so we want delta S to be positive. So when we are asked which of the following processes are always spontaneous, we are looking for which process has an enthalpy being negative and an entropy being positive. Alright, so let's see here. In this case, we're going from 3 molecules of gas. In any case, it's from 4 molecules to 5, and even that, the 5 molecules are gas while this molecule is liquid. Definitely this entropy is positive. What can we say about the enthalpy? Remember that this is a combustion reaction. You're burning ethanol liquid here. So this, as you well know, we're using ethanol for fuel. This releases heat. This is negative. Okay, so I think we already found our solution here. Let's make sure we find the other cases. Maybe there's more than one correct solution. The sublimation of dry ice, you go from solid to gas, so you know that the entropy is positive. However, to go from solid to gas, you need to provide heat. That means your delta H is positive. So this means that this will only be spontaneous at high temperatures. The freezing of water. When you go from liquid to gas, as you remember well, the entropy is negative because you're decreasing the disorder, but you need to remove heat, that is, the process is exothermic. Careful with these phase changes. We will talk about phase change in the slide that I just skipped, but sometimes students have a hard time finding out the exothermicity or endothermicity of phase change. The formation of water from its gaseous elements. Notice that in this case you have, we already wrote this equation before, you go from 1.5 molecules to 1, the entropy decreases. This is an explosive reaction. Hydrogen is actually used for fuel. That means that this is also exothermic. This means this will be spontaneous at relatively low temperatures. And again, we do not know exactly when, unless we have the actual numbers, at what temperature that may change the spontaneity. Okay, so notice that the only one in which the entropy is favorable, that is, it points to this tendency to spread out molecules, and the enthalpy points to this tendency to minimize the energy. A is the only case in which that happens. So let me go back to these kind of graphs where we can apply the Gibbs free energy when we study gas phase. In here you can see in green is the Gibbs free energy of the solid, in red is the Gibbs free energy of the liquid, and in blue is the Gibbs free energy of the gas. How should one interpret this? At temperature below the melting point, your delta G, which is the G of final minus initial, that is the liquid minus the solid, well, the liquid is the green, so liquid is larger, the Gibbs free energy of the liquid is larger than the Gibbs free energy of the solid. This means that this is larger than this, delta G is positive, the solid does not melt because this is spontaneous. So this is not spontaneous. At the temperature between these two, notice that now there's been an inversion of numbers, so still the liquid minus the solid. Now the the Gibbs free energy of the liquid, this is smaller than the Gibbs free energy of the solid. Suddenly this means that the process going from solid to liquid is spontaneous. The solid melts after the melting point. The same can be applied when you do this for vaporization. So these graphs may help us understand how temperature can change the spontaneity of process, and the change in phase is one of the simplest examples, and again I would say the most telling one.